In this lecture, we'll study computation of short circuit current using Thevenin's theorem. This method is faster and easily adapted to systematic computation for large circuit network. Computation of short circuit current using Thevenin theorem. This is easy and faster method. Now for study purpose, consider a synchronous generator. This is synchronous generator having direct axis synchronous reactance XDG, feeding power to synchronous motor through transmission line. This is transmission line reactance and this is the synchronous motor. This is direct axis synchronous reactance of synchronous motor XDM, and this is its voltage EM, back EMF you can say. Now this is the system we have to study for the computation of short circuit current. EMF induced in the generator is EG. This synchronous generator, this is the synchronous generator feeding power to the synchronous motor. This is the synchronous motor. This is EM back EMF. This is positive, this is negative, and this is the reactance of transmission line. Reactance of the transmission line is X. Current delivered to motor is I0. This is current delivered by generator to the motor through transmission line, and voltage at the terminal of the motor is V0. So this is normal voltage and normal current, you can say pre-fault voltage and pre-fault current. Suppose fault occurred at point F. This is point F, this is point G. Fault at point F at the terminal of synchronous motor. As a first step, this model we have to replace by considering transient reactances or subtransient reactances in series with voltage behind transient reactance or subtransient reactance. So this model we have to replace by subtransient reactances. So this is the subtransient reactance of generator XDG prime in series with EMF of generator EG. This is transmission line reactance X, and this is the synchronous motor terminal. Synchronous motor transient reactance XDM dash. This is in series with source EM. This is positive and this is the terminal F where the fault is occurred. So voltage at the terminal V0 and current delivered is I0. Here we have interested to determine the transient current delivered. Now if we are interested to determine the subtransient current delivered by generator, then we have to replace the steady state model by subtransient reactances. This change not disturb the pre-fault voltage V0 and the current I0. Now applying Thevenin's theorem to this model. Thevenin theorem, this is steady state model on a network, and this is transient network where we have to determine transient current. So this model is replaced by transient network. Now applying Thevenin's theorem to this model, so plotting Thevenin equivalent circuit, this is point F, source V0, pre-fault voltage V0 in series with Thevenin passive circuit. So this is the transmission line reactance X in series with transient reactance of generator XD dash. This is transient reactance of motor XDM dash. This is point F dash. This is point G. So this is Thevenin network where we have to determine Thevenin equivalent impedance. Now here resistance is neglected, so this is Thevenin equivalent reactance XTH across the fault point. So XTH is equal to, as these two reactances are in series, resultant is XDG dash plus X in parallel with XD dash M. Resultant of this will be XTH, and this is equal to XDG dash plus X multiplied by XDM dash and divided by XDG dash plus X plus XDM dash. This is Thevenin equivalent reactance of the circuit. The pre-fault current I0 not appear in the Thevenin passive network. Now consider the fault impedance ZF. Now consider ZF as a fault impedance. ZF is fault impedance. This is connected in the network like this. This is the pre-fault voltage. This is transmission line reactance in series with generator transient reactance XDG prime. This is fault point F dash. This is the synchronous motor transient reactance XDM dash, and this is the point G. This is point G. This is suppose F dash, and this is point F. Fault is occurred between point F and G. Now fault impedance is ZF, and we have to determine current delivered to fault. So this is connected across the point F and G. So this is ZF fault impedance. Now current delivered is delta G. This is delta IG, and this is delta IM, and as per Kirchhoff's law KCL, this is fault current IF, positive, negative, and V0, and this is the fault current IF. This is fault current IF. This is reference bus. This is reference bus. This is reference point. Now from we have Thevenin theorem. From Thevenin theorem, we can write fault current IF. This is equal to Thevenin voltage V0, pre-fault voltage, upon Thevenin impedance JXTH plus fault impedance ZF. This is current through fault impedance ZF. Suppose this is equation 1. Now current due to the fault in generator circuit. So current due to fault in generator circuit. This can be calculated using current division method. So from current division method, current in generator circuit delta IG, this is equal to total current delivered to fault, this is IF, into XDM prime upon XDG dash plus X plus XDM dash. This is current due to the fault in generator circuit. So this is from the current division method. So this is suppose equation 2. Now similarly current due to fault in motor circuit we can determine. Similarly, current due to fault in motor circuit, synchronous motor circuit. This is, you can determine IF minus this, or by current division method we can write formula delta IM, current in motor circuit. This is equal to total current IF into XDG dash plus X upon XDG dash plus X plus XDM dash. So as per current division method, if I want to determine current in the generator circuit, I have to determine this current first. Then by current division method, fault current multiplied by this reactance upon sum of all the reactances. Similarly, if I want to determine current in motor circuit, then total current multiplied by this reactance upon sum of all the reactances. So this is the current in motor circuit due to the fault. This is equation number 3. Now post fault current. This is post fault current. Post fault currents. IF is equal to IGF, post fault current in generator circuit. This is equal to pre fault current in generator I0 plus delta IG. This is the post fault current in generator circuit. Similarly, in motor circuit, this is IMF. This is equal to minus I0 pre-fault current minus I0 plus delta IM. This is the post-fault current in generator circuit and in motor circuit. This is equation number 4. Now post fault voltage. Post fault voltage. Post fault voltage, this is VF. This is equal to V0 pre-fault voltage plus voltage during the post fault. This is XJXTH into IF. So this is pre-fault voltage plus delta V, equation 5. So delta V is this. This is changed due to the fault. Now steps to compute the short circuit. Summary of all these steps. And steps to compute the short circuit current. Steps to compute short circuit current. Step number 1. In step number 1, first you have to obtain steady state solution. Step number 1 is obtain steady state solution. Steady state solution. of the system. This is from the load flow study, you can say. This is the load flow study. Then step number 2. Step number 2 is replace reactances of synchronous machines. Replace reactances of synchronous machines by their subtransient reactances. Subtransient reactances or transient reactances. And short circuit all the EMF sources. So we get Thevenin theorem, Thevenin network. So first step is obtain steady state solution for the given system. This is load flow study. Load flow. Step 2 is we have to replace all the reactances, steady state reactances, by their subtransient or transient reactances as per requirement, and short all the EMF sources. So we get Thevenin equivalent network. Now step number 3. Then excite the Thevenin network of step 2. This is excite Thevenin network, Thevenin passive network, you can say, Thevenin network of step 2 at fault point. By negative pre-fault voltage. In series with fault impedance. ZF. And after that calculate voltages and currents at all the points of interest. And step number 4, this is last step. Step number 4, calculate post-fault current and voltages. Calculate post-fault currents and voltages by adding results of step 3, step 1 and 3. Step 1 and step 3. So in step 1 we are calculating current and voltages at steady state condition, and step number 3 calculating the voltages and currents at the fault point. And then this current is added with this, we get post fault current and voltages. Now assumption here, we have to assume assumptions in the short circuit current computation. First assume all the pre-fault voltages, assumption 1, all the pre-fault voltage magnitudes of 1 per unit, all the pre-fault voltage magnitudes of 1 per unit, and all second assumption, all pre-fault currents are 0. So this way we can calculate the short circuit current of the given network using Thevenin theorem. Thank you.